Colin Hindle to come back for his second presentation. Colin is going to talk to us about polymers in photonics and electronics.
It's a slightly strange title line up for me. Quite a challenge to address in 20 minutes, but I'm going to give it a short shot. So, I'm going to try and cover very briefly some aspects of the conductivity range of polymers, a little bit about PN junctions, I'll explain that, licensing devices, particular polymer licensing devices, displays, a little bit about energy saving, and trying to come to some very quick conclusion. Now, I'm sure I don't need to remind you of basic physics of conductivity, but maybe I need to remind myself. Of course, if you've got a wire or something, the actual resistance that you measure depends on the length of the wire, and it's inverted proportional to the area of the wire as well. And of course, the basic resistance, resistivity is what we're looking at. The conductivity is quite simply the inverse of that. So just to remind you, that's why it's got, it always seems to be funny units. So ohms to minus 1, centimeters to minus 1. Now, for the first 100 years, perhaps, of polymers, we could debate whether that's 75 years, like we care for 100 years, but for the first 100 years or so of polymers, up till very recently, polymers were used for their electrical insulation properties, and they still are used for electrical insulation properties. This whole electronic device today is only working because of the insulation through cables. But the discoveries in the last 20 or so years are starting to revolutionise that. We won't stop using polymers for insulation, but these three gentlemen here jointly received the Nobel Prize for Chemistry in the year 2000 for their work on the discovery of conductive polymers. And if you haven't actually ever met any conductive polymer yet, you can still be forgiven for that, because most polymer, thankfully, is not conductive. But when you've got conductive polymers and insulating polymers, it allows you to make some quite interesting products. There are a number of ways to increase the conductivity of polymers, and obviously some of them have been around for an awful long time. Pyrolysis was used by Swan and Edison in their early attempts to make light bulbs. They tended to take cotton and pyrolyze it to make a crude form of carbon fiber, if you like, which glows in the dark when you put a current through it. But we're also looking at how you can control the conductivity of polymers using chemical dopants in a way which is analogous to silicon wafer technology. Also, we shouldn't forget that conductive polymers are also used in conductive adhesives. In fact, one of my colleagues has done a lot of work on conductive adhesives. Being from Napier University, logarithmic scales are what we're brought up on. Of course, this is log to the base 10, which are going to make it easy to understand. So every time you do one digit, it's a tenfold increase or decrease. Depending on where you start the scale, it goes right up to the very top, 10 to the 26 or thereabouts, which in that value we're in superconductors. Polymer is not generally very good at that. Right down at the bottom, 10 to the minus 16, we've got polymers like polyethylene, which are very, very good electrical insulators. In between, we've got polymers like nylon, which are a bit more polar and not quite so good, materials like glass, cotton, polymer, and silicon devices. But by using doped conductive polymers, we can use quite a broad range of conductivity. We can actually span the area that doped silica occupies in the electronics industry. So plastics electronics is not a joke. I think when I was a student, you probably would print that down as your occupation for a joke. Plant electronics or plastic electronics would be a topic. But it is a reality, one which is rapidly becoming a commercial reality. It's the flexibility of the polymer structure that allows you to change the properties. In essence, you have molecules which are alternating single bonds and double bonds, and the delocalized molecules always conduct their mission. But you're able to change the band gap in these to make it easier or not too easy for those electrons to flow. And Peter and I already showed from the same picture that we're all actually waiting for these devices. This is plastic logic electronic book. The other area is that you don't have newspapers, you just download it from the Wi-Fi. And They promised about 18 months ago that we have one right now. The last time I actually was told it was 18 months away. But now I'm not getting it free, now I have to buy one. I don't know why. But it's a display side that would at the moment be Polymer. They're not suggesting it will replace the microchip that displays information, or not yet anyway. How do these sort of things work? They work by using incredibly complicated, weird, as a chemist, incredibly complicated molecules, which in a nutshell push electrons in or pull electrons out on the structure, and are able to produce electrons very easily. And to make light, for example, we need to combine both electrons and holes, which are positively charged species of light, to generate light. So we've got P and N type polymer. If you think about that, the N type produces electrons in light, and the P type produces a hole. That contrasts entirely with the metal film conductive adhesive type idea, where simply all you've got is a conducting of metal and making sure that you don't have very big gaps. The metal particles don't actually need to touch, but it would be very nice if they did. But as long as they get close enough together, the electrons will jump, if you like stepping stones. Physicists call it percolation, or cycling from stepping stones to get across the river. And these materials are used, particularly for flexible electronics, with electrical contacts, and also increasingly to replace lead solder, because lead-free solder requires something higher temperature, and that's not very good for a plastic substrate. So what's really new in this area are things like PN junctions being made from polymer, using photodiode. The UK is not the only operator in this global field, but it is an area. It's one where we've had a number of good research projects. Essentially, anybody can make an electroluminescent device. Making one that lasts more than a few days is a challenge. Making one that lasts a year or two is a real challenge. Essentially, you build up, usually starting from either a piece of glass or a piece of plastic as your transparent substrate. You put a transparent conducting anode on it, almost always using tin oxide. Then you deposit the P-type polymer in the N-type polymer. And finally, we use what's called aluminium as a cathode on it. And then it will produce light in the middle by the collision of electrons and holes, generate light, the light will reflect it from the back cathode into the front of the screen. In essence, it's as simple as that in theory. What's really happened, of course, is dependent on the energy levels in the various materials, and you've got to get these actual holes and electrons to come together and crash right in the middle of the salmon structure that you want to produce. And calcium is very commonly used, so one of the biggest problems with any of these devices is permeability to moisture. If you build it out of glass, that wouldn't be a problem, but if you use a polymer which is relatively flexible, then permeability to moisture destroys these devices with the reaction of calcium. Oxygen is also a bit of an issue. So these devices, being as displays, can and are just about being produced, particularly like Cambridge, like Cambridge display technology, by printing polymers from special printing units. The sort of polymers that are involved here typically cost about £1 million a tonne, actually, a bit more than £1 million a tonne. So it's a bit off-putting, but you've got to remember, people making these products do not buy a tonne. And in fact, a very big order would be to buy 10 grams. Most people I know buy 1 or 2 grams. Yeah? That's expensive enough. Because a little goes a long way. A little can go a very long way if you make the device very, very small. This is an example of a micro display, which you may not have seen, unless you've got a manual